Okay guys, next we are going to talk about triple integral in a spherical coordinate system. So you suppose that we are using a spherical coordinate system. So we have a function of rho phi theta. Remember here they mention rho theta phi, but actually nothing wrong, but usually rho comes first, phi second, third, theta. So rho phi theta dv on a region D. So you can see our region D here. Okay, first of all, let's see that what is dv in a spherical coordinate system. We know that dv in Cartesian coordinate system is dz dy dx. In cylindrical coordinate system is r dz dr d theta. But as you can see here, dv, you see some calculation, you may read it, but it doesn't matter. You just bear in mind what is dv here. dv equals rho squared sine phi, rho squared sine phi d rho d phi d theta. Okay, so we put it here in the integral. So you can see f, and this is dv, rho squared sine phi d rho d phi d theta. So of course this is not the only order, but usually we set up in this course for you, the integral will be set up in this order. And okay, so you can see here totally we have a function of rho phi theta. So starting with, first we integrate with rho, then with respect to phi, then with respect to theta to find the answer. Okay, but if you wonder where this rho squared sine phi is coming from, soon later when we are talking about the substitution in triple integrals, you are going to know that where this rho squared sine phi is coming from. So for now, just bear in mind that d phi equals this. Next, we are going to see that how we are going to describe the region D in a spherical coordinate system. Okay, look at the next page. Listen very carefully. So according to this, it means first we are going to find the limits for rho, then for phi, then for theta. Look at here, let's say this is our boundary region D. So when we have a boundary region D, so usually let's say we have a surface from below which is nearer to the origin, and from above, something like that, we have another surface which is located further to the origin, So now we have to mention the equations of these two surfaces, the one nearer and the one further, such that rho is a function of phi and theta. Do you remember, like when we are using Cartesian, like we have a lower surface, upper surface as a function of x and y. So here we have two surfaces, one nearer to the origin, let's call it inner radius. The one further to the origin, let's call it outer radius. The equation of inner must be mentioned such that, because we are using a spherical coordinate system, such that rho is a function of phi and theta, like g1 of phi and theta, and the further one or outer radius, rho equals g2 of phi and theta. So to cover the region D, we say, okay, rho is from inner radius to outer radius. Okay, this is for rho. And then look at here, look at the next page. We have to see, to cover the region D, what is the minimum amount and maximum amount, actually two angles, to cover the two angles, to cover the region D. You can see here, we have like here, phi is like, let's say phi minimum, and here is phi maximum. It means to cover the region D, phi must rotate from this to this. It means from here to here. It means from phi minimum to phi maximum. between two angles. Okay, so phi must be from phi minimum to phi maximum to cover the region D. To cover the region D like this. And then, okay, these are the limits for phi. Then you look at the image of region D on 2xy plane, which is a two-dimensional region here, R, let's say R. Then you have to see, to cover the region R, what is the minimum and maximum amount for theta to cover the region R here. This region R is the image of D on 2xy plane. So we can see, to cover the image of region D on 2xy plane, it means this one, theta must rotate from, or must move from alpha to beta. So we have theta between alpha and beta, or theta is from alpha to beta. So now we can set up the integral like this. You can see rho from g1 of phi and theta to g2 of phi and theta. Here again they said theta and phi and theta. Phi from phi minimum to phi maximum, two angles. Okay, you can say from phi is from, for example, okay, sorry for interruption, phi is from gamma to delta, something like that, two angles. And theta is from alpha to beta. So this is our f and this is our d phi. So we start first integrate with respect to rho, then with respect to rho first, then with respect to phi, then with respect to theta, we will find the answer. So you can see here they mention, do not forget rho square sine phi. Now next we have an example. So do not worry, I mean here there is an example, and then later I will give you some example more provided by myself. Okay, now look at this example. Yes, okay. We want to find the volume of an object covered by the surface, these two surfaces. And you can see the equations of these two surfaces are given in a spherical. Rho equals 1 and this cone phi equals pi over 3. We know that rho equals 1, it means a circle centered at origin of radius 1, and phi equals pi over 3 is a cone. So you can see here. So actually the object or the region, like from the below, is covered by this cone, and from above by this sphere. So this is our object actually, you can see, three-dimensional object. So we want to find the volume. Okay, we want to find the volume of this object. So do you remember, if you want to find the volume of an object in three-dimensional space, let me just remind you, the volume, okay, the volume will be, okay, the volume will be triple integral on d phi, right? We already mentioned about this. Okay, so since we are going to calculate this triple integral in a spherical coordinate system, this d phi will be, you can see here, this d phi will be rho square sine phi d rho d phi d theta. Okay, this is d phi. So this volume you can see. And now we have to describe the region D, right, in a spherical coordinate system. So you can see, to cover the region D, I can say rho. You know that what is rho? Rho is the distance between any point inside region D to the origin. The distance between any point and the origin. So rho is from 0 to a sphere, okay? But what is the spherical equation of the sphere? Rho equals 1. It means rho as a function of phi and theta is a constant function. So rho equals 1. So we can see here. Rho is from 0 to 1. Now, to cover this region D, what is the rotation actually for phi? Okay, we know that if we have any point here and we have a line segment between this point and the origin, phi is the angle between this line segment and the positive direction of z-axis. So you can see, to cover the region D, phi is from 0 to what it established, okay, what is going to stop this rotation? The cone. So phi is from 0 to pi over 3. So phi is from 0 to pi over 3. So you can see when we start the rotation, what is going to stop this rotation is the cone. So phi is from 0 to pi over 3. Okay. So now, so phi is from 0 to pi over 3. Now look at the projection of region D onto xy plane. So the projection of region D onto xy plane will be a circle, right? Will be a circle. To cover this circle, theta must be from 0 to 2 pi. So these are the limits for theta. So now the integral is set up correctly, we are going to solve it. Okay. Look at here, the first integral with respect to rho. So we have rho squared d rho. So integral of rho squared d rho is rho cubed divided by 3 from 0 to 1, which is left 1/3. You can see here 1/3. So this 1/3 is a constant. Now next we have to integrate with respect to sine phi. Integral sine phi d phi equals, minus cosine phi from 0 to pi over 3. So if we calculate it here, okay, I think I need to calculate this one for you here, this one, to know that why we get this. So we have minus 1/3 cosine phi from 0 to pi over 3, okay, and this equals minus 1/3, okay, cosine pi over 3, it means 60 degrees is 1/2. It's 1/2. It's 1/2 minus cosine 0 is 1, and then so you can see here 1/2 minus 1 is, okay, we have minus 1/3 times minus 1/2, correct or not? So minus 1/3 times 1/2 minus 1 is minus 1/2. So the answer will be 1/6. So the answer must be 1/6. The answer must be 1/6. Yes, it's correct. Okay, because yes, if you can calculate here, and here, this time this become minus 1/6 plus 1/3. You can see here. So the answer will be 1/6, as I calculated here for you, 1/6. So this will be 1/6, okay, 1/6. This is 1/6. So the last integral, so this is 1/6. The integral from 0 to 2 pi d theta is simply 2 pi. It's because it's theta from 0 to 2 pi, so 2 pi minus 0 only left 2 pi. So 2 pi divided by 6 is pi over 3. So the volume of this object is pi over 3. Again, the answer cannot be negative because we are calculating volume. Okay, look at the next page here. We have talked about this and the summary of the discussion on Cartesian, cylindrical, and spherical coordinate system. Here you can see the formulas that we can go from cylindrical to Cartesian, from spherical to Cartesian, from spherical to cylindrical. So we have talked about this, so I leave it to you. But the main point here is that do not forget that d phi in Cartesian is dx, dy, dz. In spherical is rho square sine phi d rho d phi d theta, and in cylindrical is dz r dr d theta, which is equal to r dz dr d theta. Do not forget about these things. Okay guys, next we are going to talk about substitutions in triple integrals, which is very important. So listen very carefully. Let's say we have a triple integral f of x, y, z dv, dx, dy, dz in Cartesian coordinate system on a region D. Just like single integrals and double integrals, we can use substitution for triple integrals to make the calculations easier. You can see here they said we can use this substitution x, y, and z as a function of 3 new independent variables u, v, w. But let me explain you by some graph what it means. Look at this graph. Actually, when we are using substitution in triple integrals, it means actually we have two three-dimensional space. Here we have one three-dimensional space represented by x, y, z, and here we have another three-dimensional space represented by u, v, w. So we have two three-dimensional spaces. So look at here. Here we have a region G in this three-dimensional space, and here we have this region D in this three-dimensional space. So when we say we are using this substitution, it means actually we have an one-to-one map or mapping from here to here. Okay, that okay, what is that map? That map is given by these equations. Okay, that when we use this substitution, the region G in three-dimensional space represented by u, v, w is mapped to this region D in this three-dimensional space represented by x, y, z. Okay, so we have a map from here to here, and conversely from here to here, because it's one-to-one, which maps G to D by these equations. Okay, by these equations. So of course, I mean, when we use substitution, the calculation might get easier, and also we might get easier region for integration. So let's back here. So here in the function, when we put the value of x, y, z in terms of u, v, w, so this will be converted to a function of u, v, w. You can see x is this, y, z. So you will get a function of u, v, w. So the integral of f dx, dy, dz on D equals a new triple integral with respect to an equivalent triple integral with respect to u, v, w on region G, du, dv, w. later we can decide about the order of integration when we describe the region D. But do not forget, just like double integral, we have an element here. This is the absolute value of J of u v w. This is the Jacobian of the substitution. And what is it, the Jacobian of substitution? Here you can see it's a determinant 3 by 3. So the first row, the partial derivatives of x with respect to u v w. Second row, the partial derivatives of y. And the third row, the partial derivatives of z, which might be denoted by this symbol also. So we have to calculate this and then put it here, and this is absolute value. And then when we describe the region G, then we integrate first with respect to u, then with respect to v, then with respect to w to find the answer. Okay, so do not forget. Now look at here. Look at here. If you remember, last time we talked about the triple integral in cylindrical coordinate system. But when we say triple integral in cylindrical coordinate system, actually we are using cylindrical coordinate system for our substitution. It means you can imagine that we have a x, y, z space, or we have a three-dimensional space represented by x, y, z, and then we have another three-dimensional space represented by r, theta, z. Okay, so when we say x equals r cosine theta, y equals r sine theta, and z equals z, it means we are actually using a substitution. We are using cylindrical coordinate system for our substitution. Okay, so what is the Jacobian of this cylindrical coordinate system or cylindrical substitution? Okay, j of r theta z. Okay, the first row, the partial derivative of x. Look at here, the derivative of x with respect to r, the derivative of x with respect to theta, derivative of x with respect to z, which is 0. Here, the partial derivatives of y with respect to r, theta, and z. And third row, the partial derivatives of z with respect to r, which is 0. Look at here. With respect to r, 0, and with respect to z, 1. And when we calculate this, becomes r. Look at here. So the Jacobian of a cylindrical coordinate system, or when we are using cylindrical coordinate system for our substitution, the Jacobian is r. And look at the next page. So this is a triple integral in Cartesian system. So we use cylindrical coordinate system for our substitution. So when we put the value of x, y, z in terms of r, theta, z, so x is r cosine theta, y is r sine theta, z is the same. So we get a function of r theta z here. And look at here, the absolute value of the Jacobian, and the Jacobian is r. Okay, and usually we try to choose r positive so we can remove the absolute value. So it becomes r dz dr d theta. So this is d phi in cylindrical, right? So now you know why d phi in cylindrical equals r dz dr d theta. This r is coming from Jacobian. And of course, when we describe the region G, then we can calculate this integral first with respect to z, then with respect to r, then with respect to theta. Another point. Okay, another point. You remember for three-dimensional space, we have another coordinate system, which is called a spherical coordinate system. And do you remember that we said, okay, we can calculate a triple integral in a spherical coordinate system. Actually, when we are calculating a triple integral in a spherical coordinate system, it means actually we are using a spherical coordinate system for our substitution. So actually x, y, and z, each one are a function of rho phi theta. You can see here, x, y, z. They are all functions of rho phi theta. So this is x, this is y, this is z. Now let's calculate what is the Jacobian of a spherical coordinate system, or when what is the Jacobian of this substitution. It means when we are using a spherical coordinate system for our substitution. So J of rho phi theta, okay. The first row, the partial derivatives of x with respect to rho phi theta. Second, the partial derivatives of y with respect to rho phi theta. And the third row, the partial derivatives of z with respect to rho phi theta. So it's easy. You can calculate here, okay. And the determinant will be rho squared sine phi, right? Rho squared sine phi. Now you know where this rho squared sine phi is coming from. Do you remember when we were talking about the triple integrals in a spherical coordinate system? For d phi, we said is rho squared sine phi d rho d phi d theta, right? So now you know, rho squared sine phi d rho d phi d theta. So actually this rho squared sine phi is the Jacobian of a spherical coordinate system when we are using a spherical coordinate system for our substitution. So look at the next page. Yes, here. So we have this integral f of x, y, z, dx, dy, dz on D. So we are using a spherical coordinate system for our substitution. We put the value of x, y, z in terms of rho phi theta. So we get a function of rho phi theta, d rho d phi d theta, and the Jacobian of a spherical coordinate system when we are using a spherical coordinate system for our substitution is rho squared sine phi. And we don't need to put absolute value. We can remove the absolute value because rho squared is non-negative. How about sine phi? Phi is between, okay, c is between 0 and pi, or more precisely, phi is from 0 and pi. And from 0 to pi, sine is positive, okay? From 0 to pi, sine is positive, so we don't need to put absolute value. So you can see we have the triple integral h of rho phi theta, rho squared sine phi, d rho d phi d theta on G. It means under this substitution, region D is mapped to region G in this three-dimensional space represented by rho phi theta. So when we describe the region G, then we can start integration first with respect to rho, then with respect to phi, then with respect to theta. Okay, you can see next we have an example, but before that I have provided an example for you. So first we discuss that one, then after that we will discuss this example. Okay, look at this example. We have a triple integral of 1 over x squared plus y squared plus z squared d phi on D. Okay. What is D? Okay, look at this picture. We have a cone here. The equation of this cone is z equals the square root of x squared plus y squared. Once we cut this cone with this plane z equals 1, the other time we cut this cone by this plane z equals 2. So the region D is here actually, inside cone between these two plane actually. Okay. To calculate this triple integral on region D, we are going to use a spherical coordinate system for our substitution. You can see this is x, this is y, this is z. So of course when you are using a spherical coordinate system, it means you have to describe the region D using rho phi theta. So when you describe it using rho phi theta, this will be the description of region D using rho phi theta. So in the equivalent integral with respect to rho phi theta, we use the description of D using rho phi theta for our integration. Okay, look at here. To cover the region D using rho phi theta, as I mentioned, every surface must be converted to a spherical. First of all, if you remember, we have done this. The spherical equation of this surface is phi equals pi over 4. We have done this. And now look at here. Sorry. Look at here. Rho is from z equals 1 to z equals 2. Okay. Rho, look at here. Rho is from this plane to this plane. The plane z equals 1 to z equals 2. So it means this is the surface nearer to the origin and this is the surface further to the origin. We have to find the spherical equation of these two planes. I have done here for you. Z equals 1. We know that z is rho cosine phi equals 1. So if we divide both sides by cosine phi, we have rho equals 1 over cosine phi. So rho equals 1 over cosine phi is the spherical equation of this plane. Similarly, z equals 2. Z is rho cosine phi equals 2. So rho equals 2 over cosine phi. So 2 over cosine phi is the spherical equation of this plane. So we can say rho is from, look at here, from this plane. What is the spherical equation of this plane? 1 over cosine phi. So rho is from 1 over cosine phi to the spherical equation of this plane, which is 2 over cosine phi. So rho is from 1 over cosine phi to 2 over cosine phi. Do you remember rho is between two surfaces? Each surface is a function of phi and theta. Okay, here it happens that these two equations are independent from theta, but totally we are viewing these two as a function of phi and theta. So rho is from 1 over cosine phi to 2 over cosine phi. Now, to cover this region D, what is phi? Okay, phi is from 0 to the cone. What is the equation of the cone? Pi over 4. So phi is from 0 to pi over 4. Phi is from 0 to pi over 4. This is for phi. Now, what about theta? Look at the image of region D on 2xy plane, which is a circle. So to cover this, theta must be from 0 to 2 pi. Okay. So now we are ready to solve the integral. Look at here. So we put the value of every term in terms of rho phi theta and the Jacobian and region G, which is the image of the region D under this substitution. It means for the new integral, G must be described using rho phi theta. You can see here. So this is for rho, this is for phi, and this is for theta. These are actually the description of region G. Okay, in region G in three-dimensional space, rho phi theta. You can see here. This is D. Okay, 1 over, you know that x squared plus y squared plus z squared is rho squared. Do not forget the Jacobian and then d rho d phi d theta. Now, what is the Jacobian of a spherical coordinate system? Is rho squared sine phi. So remember, in the exam, you don't have to calculate it again. You just put J of this spherical coordinate system, rho squared sine phi. So I'm gonna do it here for you. Now look at here. So we have integral. So 1 over rho squared and this Jacobian is rho squared sine phi. As I said, this is always positive. We don't need to put absolute value, so we can remove the absolute value. So this is the Jacobian, d rho d phi d theta. So rho squared divided by rho squared is 1, so only left integrals sine phi d rho d phi d theta. Okay, so now first we are going to integrate with respect to rho, then with respect to phi, then with respect to theta. So the first integral with respect to rho, this sign feels just like constant. So the integral of d rho is rho from this to this. So let's move up here. We have to do it here. The space is not enough. I have to erase this. So the first integral with respect to rho, integral d rho is rho from 1 over cosine to 2 over cosine. So this equals sine phi times, okay, the value of rho, when rho equals 2 over cosine minus when the value of rho equals 1 over cosine. So we can see 2 over cosine minus 1 over cosine d phi d theta. So this equals integral, look at here, 2 over cosine minus 1 over cosine left 1 over cosine times sine. So we have sine phi over cosine phi d phi d theta. Now look at here, this sine phi over cosine phi is actually tangent phi. But if you want to solve this integral, okay, if you want to solve this integral, use substitution. You take sine phi to be u. It means, okay, let me just quickly write it here for you. If you want to solve this integral, you use this substitution. You take u to be like sine phi, okay? You take u to be sine phi. By this substitution, okay, by this substitution, you take here for integral sine phi over phi d phi, you use this substitution. You take u to be sine phi. Hold on a second. No, sorry. You take u to be cosine phi, okay? Let me correct it. You take u to be cosine phi. Okay. Okay, use this substitution. You take u to be cosine phi. If you use this substitution, so the answer to this integral will be minus ln the absolute value of cosine phi. Phi is from 0 to pi. Okay, so equals integral from 0 to 2 pi minus, okay, ln cosine when phi equals pi over 4, so you can see minus ln the absolute value of cosine pi over 4 minus ln cosine when phi is 0. Okay, so we have to calculate this. Since the space is not enough, let's move up here. Okay, look at here, let's move up here. Integral minus, okay, ln absolute value of cosine pi over 4. Cosine pi over 4 is this, 1 over the root of 2. Okay, 1 over the square root of 2. And it's positive, we don't have to put absolute value. So minus, okay, so this one equals ln 1 divided by the root of 2. And here, minus ln the absolute value of cosine 0. Cosine 0, you can see here, cosine 0 is 1. Okay, cosine 0 is 1, so ln 1 is 0. So this is gone, only left is minus ln cosine pi over 4. So it's this here, d theta. And this equals, okay, this is a constant. By the properties of logarithm, this minus ln equals ln 1 over the root of 2 to the power of minus 1 by the property of the logarithm. And integral d theta is theta from 0 to 2 pi. So this equals 2 pi and this equals ln the root of 2. Okay, so 2 pi times the ln the root of 2. This is the answer to this triple integral on this region D using the spherical coordinate system for our substitution. Okay, now here we have an interesting example. We want to use substitution to calculate this triple integral. Triple integral of 2x minus y divided by 2 plus z divided by 3 dx dy dz over region D, and you can see the description of region D. X is from y over 2 to y over 2 plus 1. It means from, you can see here, from this line. Okay, sorry, I said from the line, from the surface actually. Look at here, from the surface or plane actually. X equals y over 2. Look at here, this is the you have to view this equation in three-dimensional space. So y equals 2x, or equivalently x equals y over 2 actually is the equation of this plane here, this one on the back. So in the front we have this plane, y equals 2x minus 2, or equivalently x equals y over 2 plus 1. So we can say x is from, so it means here x is written as a function of y and z. Okay, this is another order. So x is from, like for x, lower surface to upper surface. So the lower surface, okay, for x is this, x equals y over 2. Upper surface for x is y over 2 plus 1. So you can see x is from lower surface to upper surface for x, okay, because this time x is a function of y and z. So now if you get the image of D onto YZ plane, the image of D onto YZ plane will be a rectangle. So you can see y is from 0 to 4 and z is from 0 to 3. Okay, so we are going to use this substitution to calculate this integral. So of course we substitute the value of x, y, z. So here we get a function of u, v, w, and we have to calculate the Jacobian, and then we have to see under this substitution what is the region G in UV plane that we have to integrate on. So you can see the answer is given here. So it means if we use substitution, the region D is mapped to region G in UV plane, which is a rectangular region. Very easy. You can see V is from 0 to 2, U is from 0 to 1, and W from 0 to 1. But if you wonder how we get G, I mean, under this substitution, you may wonder why G is like this, how to get G. Of course, I understand it might be difficult for you, but do not worry. I try to explain for you, and you should see some more examples, then should be fine. Look at here. You have to find the limits, it means lower and upper limits for u, v, w using these three equations. It means first you try to find, okay, here you can see x, y, z are function of u, v, w. You try to find u, v, and w, it means inverse, as a function of x, y, z, and then you use the limit of x, y, z to find the limit for u, v, w. What I mean is this. Look at here. I prepared for you here. X equals u plus v, y equals 2v, z equals 3v, right? Okay. Look at here. Let me start with this 2. So if you divide both sides by 2, v equals y over 2, right? And if you remember, let's back to this integral, y is from 0 to 4, right? So y is between 0 to 4, so you divide both sides by 2, so y over 2, which is v between 0 and 2. So these are the limits for v, from 0 to 2. Similarly, z equals 3w, right? So if we divide both sides by 3, w equals z over 3. So again, back to this integral, look at the limits for z. Z is from 0 to 3, right? So back here, z is between 0 and 3, so if we divide both sides by 3, we have z over 3, which is w between 0 and 1. So you can see v between 0 and 2 and w between 0 and 1. But the things for u are a bit more complicated, but I'm going to explain for you. Look at here, from this equation, x equals u minus v, right? From this equation. and v equals y over 2. So we have x minus y over 2, which is 2x minus y over 2. Now look at the next page. So u equals 2x minus y over 2, right? Okay. Look at here. If you back to the picture, we have two planes here. This one in the back is y equals 2x. This one in the front is y equals 2x minus 2. Okay. So we have y equals 2x, the plane in the back, and the plane in front, y equals 2x minus 2. So these two are equivalent to saying that 2x minus y equals 0 and 2x minus y equals 2. Now let me divide both sides by 2. So we have 2x minus y divided by 2 equals 0, and 2x minus y divided by 2 equals 1. But what is this 2x minus y divided by 2? Is the u. So this is equivalent to saying that u is 0. This is equivalent to saying that u is 1, because this is u. Look at here. This is u. So it means when you say, okay, x is between the plane on the back to the plane on the front, okay, so it means we are moving from plane y equals 2x to the plane y equals 2 minus 2, 2x minus 2. This is equivalent to saying that u is from 0 to 1. So in total, you can see here. So now it should be clear for you why u is from 0 to 1. So you can see y is like that. Why is it like that? U is from 0 to 1, v is from 0 to 2, w is from 0 to 1. So this will be region G for our integral with respect to u, v, w, as I calculate here for you. You can see for u and for v and w. Okay. Now let's back to the calculation of the integral. Okay. Now let's calculate the integral. Yes, let's move on to this page. Okay. This is our integral, right? F of x, y, z, dx, dy, dz. It's easy to calculate. This is our f, 2x minus y divided by 2 over z over 3. Actually, just now I calculate 2x minus y divided by 2 is u, and z over 3 is w. So we put it here. Okay. And then we do not forget the Jacobian of the substitution, du, dv, dw. We can solve in this order because G is rectangular. But what is Jacobian? Okay, Jacobian. The first row, the partial derivatives of x, y, z. So look at here, x is u plus v, if you remember. Derivative of x with respect to u, 1. With respect to v, 1. With respect to w, 0. Y is equal to 2v. So the derivative of y with respect to u, 0. With respect to v, 2. With respect to w is 0. This one is this row, partial derivatives of z. Z equals 3w. So the derivative of z with respect to u, 0. With respect to v, 0. With respect to w, 3. So this is like a kind of, if you view it as a matrix, it's like triangular, right? So the matrix, so the determinant of this matrix, this determinant will be the product of diagonal entries. So if we calculate, this equals 6. Okay. So you can see here we put. So this equals u plus w is here. And Jacobian is 6. We don't need to put absolute value. We can remove. du, dv, dw. And this is the description of region G in u, v, w. U from 0 to 1. V from 0 to 2. And w is from 0 to 1. Okay. Now we are going to calculate this. I'm going to do for you. Okay. So let's continue to solve this here. So you can see here the integral 6 times u plus w. So this equals 6 times integral u plus w du d phi dw. So this equals the first integral with respect to u. Okay, so the integral of this term with respect to u. So the integral of u is u squared divided by 2, and w is constant, becomes wu. Okay, from 0 to 1. So when u is 1, this becomes 1/2 plus w. When u is 0, this is 0. So only left this. So 6 times integral 1/2 plus w d phi dw. So the next integral with respect to v, but this one is constant, right? So the integral d phi is phi from 0 to 2. So when phi is 2, this equals 2 times 1/2 plus w, and when v is 0, this is 0. Okay, so left only this. 6 times integral from 0 to 1 dw, and this equals, look at here, 6 integral from 0 to 1, this equals 2 times 1/2 is 1, 2w. Now this integral with respect to w, we have the 6 equals 6. The integral of 1 is w. The integral of 2w is w squared from 0 to 1. So becomes 6 times 1 plus, when w is 1, this becomes 1 plus 1. When w is 0, this is 0. So becomes 6 times 1 plus 1, which is 12. So 12 is the answer to this integral. You can see the answer is not given, but we have done it for you. So the answer to this integral becomes 12. Okay, you can see we are done with this chapter, and at the last page of this chapter we have some exercises. They are very interesting, so I strongly recommend you to spend some time and try to work on these exercises. Okay, all of them, very interesting.